I mean, he didn't even know his part.
All right, so
Memorize my speech.
let's get started. Jump back into those guided notes that you received yesterday. Again, if you need a copy because you weren't here, they are sitting in front of the desktop over there behind the link. If you are at home, check yesterday's announcement. The link is right there. Yeah.
Are you gonna be here tomorrow?
Yes. Tomorrow morning I will be here. Tomorrow afternoon I will not. At least that's the plan.
Us three have an AP witness, but I'm not sure when it finishes.
Yeah, I'll be there too.
Okay.
Oh, yeah.
Yeah, the half of your class will be gone.
That's fine. We'll keep rolling on for sure. And Thursday will be a day where we recap and practice.
Okay, I was gonna say that's.
So like yesterday was like learn it for the first time and do like one or two together. Today is a recap and practice day. Tomorrow we'll kind of do the same thing with what's next. So we'll learn like how to use this idea tomorrow, and then we'll practice Thursday. Friday will be the day where I'm not here, so I will. There's plenty of practice in here, so Friday will just be a practice day. Obviously, seniors, you guys are done Thursday, so that's upside. But seniors, just make sure that I sign your checkout form before you leave on Thursday. Okay, because I'm not here Friday. I know you aren't either, but barbecue's here and all sorts of other things. So what I want to do today is jump back into here, bottom of page 250, I think. Page 250. We did the top one, top left. I want to kind of recap our process, talk through it a little bit, do at least a couple together, okay, and then give you a chance to try a few on your own, making sure that I know you're not going to master this idea in just a couple days. That's okay, because what we'll do the rest of the week is apply the same principles to new equations, and so you'll get better as we go. But for me, my focus with underclass, anybody that's not a senior, is to give you as much of Chapter 4 as I can, even if it's just at surface level, so that you're exposed to it for the first time. If you go back to AB, you will see this stuff again. If you're going through BC, you'll have a better chance of those first couple weeks in BC, or maybe like your summer work for BC, being a little bit more familiar to you. But either way, expect something usually over the summer, just as you probably have for the last couple years. So really quick recap. I'm just going to write it over here since we already did this one, of how to deal with equations that are given to us that are just not like, just not functions, right? I just can't get y equals a function of x. Can't do it. Right? Maybe it's because if you look at this first one that we did together, there was a y squared and a y. Can't isolate y. If you look at this next one, there's an e to the y and there's a y squared. There's no way for me to get y by itself. But we still can find dy dx, and that's kind of the goal here. And what we saw yesterday was a really good plan was first taking the derivative with respect to x of both sides. Okay. Individually taking d dx of the left side, taking d dx of the right side, and just kind of seeing how it plays out. And so let's do that. Let's do this one. I'm going to take d dx of 2x plus e to the y. And that's going to be equal to d dx of x squared minus y squared. And this is step number one, but as part of this process, we kind of have to slow ourselves down a little bit and decide, how am I supposed to do that? How am I going to take the derivative of 2x plus e to the y? How am I going to take the derivative of both sides if I've got a couple things being added or a couple things being subtracted, or maybe there's a product or it's a whatever? I just have to kind of go as slowly as possible, realistically. And if you've got more than one term on one side, and eventually you don't actually even write this step out, but I want you to see it, you can take the derivative of each one separately, where the sign in between is just what's going to connect it. And we've been doing this for a long, long time, taking the derivative, kind of using power rule kind of stuff. So I'm going to put a minus at the end in front of that last d dx of y squared, because it's x squared minus y squared. I could do like plus and then put the negative inside, but why, right? Why drive me so crazy? Take the derivative of each one separately. And what we saw yesterday in the handful of problems at most that we actually had a chance to do is once we got to this point, we're just kind of looking at every single little piece by itself, it started to get a little bit simpler, because now all I have to do is look at this first piece right there and say, okay, do my variables match? Am I taking the derivative with respect to x and there's an x inside? If the answer to that is yes, yay. Life's easy. I just take the derivative. So what's the derivative of 2x? Yay. First term done. Plus, and on we go. Right? But if we are differentiating something that has y in it instead, right? Anytime we differentiate a y term, as I guess I'll call it, our variables just don't match, right? We have a d dx of something that doesn't have x. And all that means is we've got an application really of the chain rule, like this up here, right? That little y right there. If that was just e to the x, sweet. Derivative of e to the x is e to the x, and I'm done. Really, what we've got is e to the something else. And any time that comes up, whether it's e to the x, whether it's cosine of y, e to the y, cosine of y, or even just y squared, like we'll see at the end, what we've really got is the chain rule. And what we do with the chain rule is we kind of leave things alone, and then eventually we will take the derivative of whatever that different part is, in this case, the y up there or the y in there. But as you take this derivative first, imagine, like, let your mind make it simpler for you. Treat it like you would e to the x to start. What is the derivative of e to the x? E to the x. And so when I start finding the derivative of e to the y, I'm going to write it exactly the same as I would as if it was e to the x. Okay, cool, e to the y. But what the chain rule tells me about finding the derivative of exponentials is if my exponent is more than just x, or in this case, just different than x, what I need to do is multiply by the derivative of that exponent. Right? Same thing with the chain rule, right? We leave kind of like the thing more than x alone, do whatever we need to do, and then eventually we multiply by the derivative of the inside. Right here, we multiply by the derivative of the exponent. Well, the exponent is y. How do we write the derivative of y with respect to x? dy dx. And so what we'll see happen every time, which is really, really nice, that we can kind of count on this, is that anytime we differentiate a term that has y in it, what we'll need to do is attach a factor of dy dx. Solely on the chain rule kind of mindset that it just wasn't x up there, it was just something else. And you can kind of bank on that happening, treat it like you would x, but just have a dy dx attached to it because of the chain. And if you just go one term at a time, this gets a little bit easier, and you just kind of say, okay, do my variables match? If they do, sweet, I'll just take the derivative, and I don't need this differential term. It's called the differential. I don't need this if the variables match. If they don't match, then I need. So here we are on the right side now, the derivative of x squared with respect to x. Do your variables match? Then just take the derivative. What's the derivative of x squared? 2x. And like I said, I kept the negative on the outside of the derivative rather than saying plus d dx of negative y squared. It's going to end up being the same thing anyway, so that's a good idea. But as we try to find the derivative of y squared, really in my mind, I treat it the same way I did the x squared. I'll just make sure that because my variables don't match, I'll just attach a dy dx at the end. Really what we've got is the chain rule where y is on the inside. And when I take the derivative of y squared, drop the 2 in front, leave the inside the same, decrease the power by 1, and then multiply by the derivative of the inside. Kind of a chain rule kind of thing. But really, you can just say, all right, let me treat it like x squared, and then I'll throw a dy dx at the end. So if the derivative of x squared is 2x, what's the derivative of y squared? 2y, but because it's a y, what do we got to put at the end? dy dx. And that's what I'm trying to eventually solve for. Right, that's kind of the last thing that I have to do is solve for dy dx. I got to get that differential by itself. How I do that depends on how many dy dx's there are. If there's only one, then just go get it. All right, go solve for it. Add, subtract, multiply, divide, do whatever you need to do. If there's more than one dy dx, we still want to isolate it, but it's just going to take a little bit more forward planning to get ourselves to the point where I can get dy dx all by itself. Okay, so if there's only one, just go solve for it. If there's more than one, so that's what I'll focus on here. If, I guess, there exists more than one dy dx term, okay, how do we get ourselves to the point where we can get dy dx alone?
Move all the terms onto their sides, like their appropriate sides. Like dy dx is on one side and the rest is on the other.
Good. Move all your dy dx's to one side, usually the left. I'll just say one side. I don't care which side you do it. Okay. Everything else to the other. Else to the other. Usually we just move everything to the left that has dy dx. So like e to the y, dy dx is good on the left. I got to add 2y dy dx to get it over to the left. And then move everything else to the right. Like the 2x that was already on the right is good there. I have to move this 2 over there. With subtraction, I got to move this negative 2y dy dx to the right. From the right. I don't care which side they end up on, because eventually we're just going to get all the dy dx's alone. On one side, everything else will go to the other. Now, why do that? Why are we getting all the dy dx factors, right, the terms that have that factor in there onto one side, moving everything else over? Factor it out, and then divide it away. Every time, okay? Once they're all together, now I've got a common factor. Let's factor out dy dx, and then divide. Okay, so this dy dx is going to come out. We'll be left with e to the y plus 2y, 2x minus 2, and then we can divide it away. Dy dx, 2x minus 2 over e to the y plus 2y. Once you get dy dx by itself again, that's all we need to do. Now, let me ask you this. Can we divide like this 2 right here with this 2 right there? It's not a common factor top and bottom, so make sure that we don't divide away things that we shouldn't. So this looks good. I like it. Nothing we can put together, no real simplifying that can be done. 2x minus 2 over e to the y plus 2y. And a lot of times what you'll see is that if it's not a function to start, your derivative probably isn't a function either. And a lot of times you'll have not just x in your derivative, but like y instead, or x and y. Which means if you want to find the rate of change at a certain point, you need to know the whole point, not just x. Okay, we'll plug in the x and the y wherever we need to. But that's the plan. Okay, ddx on both sides, differentiate however you need to with each single term. And whether or not you actually write out this step in red, I think is just up to you and how comfortable you are. Maybe eventually you just drop right down to that next line in blue and say, okay, I'm just going to find the derivative of 2x. Sweet. Find the derivative of e to the y, and just kind of work your way through. But that's up to you. The quickness with which you do calculus is directly proportional to how comfortable you are with the skills that you learn. If you're still not great with exponentials, with logs, with product rule, with quotient rule, you're going to want to take your time and go slowly. That stuff is starting to become easier and easier every week, every day. Then you can start to pick up the pace a little bit and be just a little bit more efficient. Questions about the plan or this example? How we're all worked out? Sweet. Let's do another one. Because what's nice about this one down here at the bottom is it kind of pushes us a little bit further. Once we take the derivative of the left and the derivative right, I think that will become a little bit more apparent. And again, I'm going to write this down. I think this is a good first step to show whoever's reading this what you're doing. Makes it super obvious where everything else is going to come from once you write, all right, I'm going to do d dx of both sides. Because what you'll see us do tomorrow, Thursday, Friday, maybe into Monday, we'll see. Is we won't take d dx, we'll take d dt or d dr or d dh or whatever it is we want to find. Now, left-hand side, there's only one term there, so I'm not going to like individually find derivatives, but I have 2x times y, two different variables in there, all being multiplied together on one side. I'm supposed to find d dx. What is it going to take for us to find that derivative on the left? That's a product of two different things, x and y. Right, and 2x times y, I think, is a good way to break that up, right? Really what's happening is that's right. We've got 2x, call that u, and y, call that v. In order to find d dx of the left-hand side, we just need the product rule. All right, so u is 2x, so du is 2. V is y. Here, I'll write it down. So u is 2x. So du is 2. V is y. And remember, when we first started to do this, I'm like, oh, I'm just going to write it as du and dv. But remember, it's du dx and dv dx, right? We're taking the derivative with respect to one variable and not another. So we want to kind of keep that in mind. And so finding du is really finding du dx. Sweet, variables match, so that's an easy one. Finding dv dx of y, variables don't match. And so we need this implicit style with the chain rule to say, okay, let me find this derivative, and then I'll attach it with dy dx to it. So what's dv then? Well, if that was just an x, if v was just x, what would dv be? 1. Okay, cool. So treat it just that same way. 1, but times dy dx, because the variables don't match. And what's 1 times dy dx? And that's eventually what I'll be solving, right? And I just need this little side work here to kind of get me started. That's the product rule for the left-hand side. And I think eventually you might even get to the point where, like, I don't need to write that down. I can just say u, okay, dv, okay, plus v, okay, du. And if you say that to yourself, I think you'll get to a point where you can do this a little bit faster. Now that's just the left side. Now we work on the right side. And again, if you want to say, okay, I'm going to do d dx of 3y squared, I'm going to do d dx of 2x, I'm going to add them together and like write that step out where you separate them, go for it. But I think we're maybe getting even just on day 2 to the point where, okay, I'll just do each one, right? Let's find the derivative of 3y squared. Well, treat it like 3x squared. That's it. Treat it exactly the same way. We'll just throw a little dy dx at the end. So what do you think? 6y dy dx. All right, drop the 2 in front, multiply them together, decrease the power by 1. Really, it's just a chain rule. Like, it's just the inside is y. Drop the 2 in front, leave the inside the same, decrease the power by 1, and then multiply by the derivative of the inside. Well, that's just dy dx. Plus, I'm just going to match that right there, the derivative of 2x. Yeah. And there it is. There's my setup. There is my differential equation. In the math world, we call those diffie Qs. Diffie Qs. Basically, that's getting us ready for Calc 3. Differential equations, diffie Qs. Now, if we only had one dy dx, I would just solve for it directly, but we have more than one. So let's get them onto the same side, move everything over, factor it out, and solve. Go ahead, try it. We've got a nice differential equation there, let's use it. Get all your dy dx's on one side, get everything else onto the other, factor, and divide. And if you can get yourself to there, then your algebra skills are good, right? Because the calculus doesn't last very long. And calculus happens early, the rest is just algebra. Yeah. Absolutely, right? But let me ask you this first. Can I divide these y's away?
Yeah.
No.
All right, let me rephrase the question. Is y a common factor, top and bottom? No. Then do not divide it away. And that's what I saw way too much of on quiz 3.2. People trying to divide away things that are not being multiplied. If things are connected by just addition or subtraction, it is not a common factor and cannot be divided away, like these y's. A lot of us would just have crossed the y's out and said, okay, I'm good. Factor first, simplify second. We can factor out a 2 from top and bottom. Let's do that. X minus 3y, divide away the 2's. So there's my dy dx, 1 over y, sorry, 1 minus y over x minus 3. No big surprise, it's got x and y in it. Whatever this crazy looking equation, I wonder what this looks like. Actually, let's see. Is it 2xy equals something? 3y squared plus 3x. 3y squared plus 2x. There you go. Pretty cool though. Funky. Yeah. Obviously not a function, right? Not going to pass the vertical line test. Some undefined spaces in there. Because maybe there just is not a pair of xy's that are going to work between like what looks like 0 and 6. Greater than 0, less than 6. And there's the derivative that says stop at any xy that you want. Plug in those values, we can get this one. Right? Because stop at 10, there's 2 different y's to go with it. So we need the y as part of our derivative. Sweet. All right, one more together. Let's do one more together. Let's do this one. ddx of both sides. Now, I know that there's more than one y in this equation, so it's written implicitly right now. But what is the power of y everywhere? What's the degree of y in every single term that has one? The same. Which means you could, if you wanted to, you could solve for y. Absolutely. If you wanted to rearrange this equation right now, like factor the y out of the right-hand side and then divide everything else away, you'd have y equals everything else. You're rational, and you just use a quotient rule, and you'd be done. You can do it. You absolutely can do it. Or you can say, you know what, I'm just going to implicitly differentiate rather than explicitly. Totally up to you. Right, we're stuck here, right? Different powers of y, we don't have a choice. Here, we could if we wanted to. So don't feel like you are stuck doing this. If you can solve it directly for y, go for it. If you can't, this is where this comes from. Okay? Now, again, I could write every little step, d dx of 5x to the third plus d dx of 3 plus equals d dx of 2, and go through it that way. I'm just going to jump in. The derivative of 5x to the third, variables match, life is good, 15x squared. Thus, d dx of 3, sweet, 0. You don't really need to write that, but just so we see. Okay, left side was easy. Variables match, they just power rule, trig, exponential, whatever it is, right? We now have all of the skills to differentiate. Okay, now we have to do the derivative of 2y. In your mind, it's just 2x, and then I'll just attach the dy here. So what is that derivative look like? Love it. 2 times dy dx. Minus, okay, I just match up the signs so I don't have to worry about like inside worrying about the sign. Now the derivative of 3x squared. What are we going to need? We need the product. Okay? And that product rule is going to happen in here. I am subtracting the derivative of all of that, which is why I like to pull the negative out, because I don't have to worry about it, but I do want to make sure that whatever I do here is being subtracted. And you just kind of have to figure out, okay, what's my u going to be and what's my v going to be, hoping to separate x and y. I want them in different spots so I can differentiate them separately. So what do you think your u should be? 3x squared sounds good. What's the v then? Perfect. One has x only, one has y only, and I can differentiate them separately. If you are still in the camp that where you want to say, okay, here's u, 3x squared. Here's du, 6x. Here's y as my v, and my dv is going to be dy dx. Great. But maybe you're starting to get more comfortable. You say, all right, cool, watch this. I'm just going to write u times dv. And you can say that to yourself. Like in your mind, you kind of say the product rule and you just go one little piece at a time, and you kind of do it as you go. Okay, u dv plus v, like for me, I like close my eyes and I just kind of picture it happening. You can start to do that if you're comfortable, if you're ready. If you are not, set up your side work, u equals v equals all that good stuff. Okay, plus v du. There we go. There's my setup. If that is too fast, then don't do it. It's okay. It's definitely not a race. Calculus is not a race. Now I'm going to clean it up, I guess. I could do a lot like quickly here if I wanted to. Let's just clean it up a little bit so we know what we're looking at. Okay, so 15x squared equals 2 dy dx minus 3x squared dy dx. And I always just leave the dy dx at the end so I don't screw that up. Minus, don't forget the minus. And then 6xy, alphabetical order there seems reasonable. Sometimes we'll have like terms, we can add them together, subtract them, whatever. Doesn't happen often, but it can happen. So you want to kind of keep an eye out for those. Where you cover up the coefficients, if everything else is exactly the same, you can put them together.
When you say negative, so in the red part.
In the red, yeah.
Minus.
So it's
the derivative of.
So this negative right here is right there.
Oh,
I pulled the negative out so that when I think about u and v, everything's just positive.
Okay.
But to do that, I had to put parentheses around the product rule.
Uh-huh.
If you were going to like keep the negative as part of u or as part of v, then that would be 2 dy dx plus, and then I would go to work on the inside. but I would probably still like use parentheses and keep things safe.
Yeah.
So I'm a big fan of whatever the sign is gonna just come in front, and then I'm gonna deal with that derivative as I go. More than one dy dx, let's get them together on one side, and then factor it out, divide it away. I love the left side, but they're already on the same side. You can flip this whole equation around and make it the left side, right? 3 equals 3 is the same as 3 equals 3, so who cares what side things are on? I'm going to move the 6xy. 15x squared plus 6xy equals, and then factor out the dy dx of what's left, 2 minus 3x. If that bugs you and you want to subtract everything to the left that needs to be subtracted, subtract everything from the left over to the right that you want to get on that side, you'll just have negatives everywhere and you'll just pull those out. However, I am still going to write it with dy dx on one side and then everything else on the right. This divided by that. 15x squared plus 6xy over 2 squared. No common factors anywhere, top or bottom. Almost had an x everywhere, but no 2 on the 2 doesn't have one. So it's stuck. No y's everywhere, no constants everywhere, so that's our best. Again, put stuff wherever you want. Move stuff around. I'm not going to stress the order at all. Obviously, look at the denominator. I didn't go like negative 3x squared plus 2. Totally up to you what you want to do there. You can pull out negatives, you can leave negatives. I just want to make sure that the implicit part of this is something. Sure. How'd you do? How's it sit? Sitting okay so far? All right. All of 251 is something I'm just going to skip over for now because it says, okay, let's find a horizontal tangent. Let's find a vertical tangent. Let's do second derivatives on the bottom of page 251. We're not going to do those just yet. Okay. Second derivative starts to come in the second half of chapter 4, so we're going to do that. I want to skip just to 252. Instead, I just want to skip one page there. We'll come back to it, maybe. We'll see. And let you take this last 15 minutes and see if you can try those 4. Okay, the first one's nice and easy. There's only one y in the whole thing, so it should be an easy way to start. And that kind of builds up from there with a couple different y's, and then into the product rule, and then into some trig. So 1, 2, 3, and 4. Okay, a good practice for you to start with implicit stuff and kind of test your chops a little bit, see where you're at. I'll put some answers up for sure, so you can see how you're doing. I'll do 1 and 2. I'll leave them up for a little bit, then I'll do 3 and 4. But now they can ask these kinds of questions on 251. Where is this thing going to have a horizontal tangent? Oh, I'll just find dy dx set it equal to 0. Where's it going to have a vertical tangent? Oh, I'll just find dy dx and figure out what's going to make it undefined. Okay. This is the notation for the second derivative, which we'll get to. But seniors, you won't see it. So now is a good time to put that in the back of your mind in case you do end up taking like a Calc 1 at some point. If you're not heading in a math direction, that'll probably be all you need to. But if you are doing something sciencey or medicine or something like that, you might end up doing Calc 1 and Calc 2. But that is the second derivative of y with respect to x squared. Okay, that's the notation. Newton's notation would just be like f double prime. Just put 2 apostrophes, 2 prime marks instead of 2. But we'll come back to that once we explore second derivative a little bit. Maybe we'll see. But let's find dy dx by implicit for these over. Yeah, sure. Easy powers for y there, so not too bad. Take my time with this one. Whatever order you write it in is okay. Just make sure your signs match up nicely. So I went a little slow to start, just so I could isolate some things. And then I picked up the pace a little bit after that. Kind of moving things around, factoring the dy dx out in the same step. So go slower if you need to. I don't know that you can go a whole lot faster than that. But we're skipping the blue line, might be enough. Or the red, pick which one you want to skip. Needed the product rule just to do it. So I'll leave this up for a couple minutes, and then I'll do 3 and 4. Those are good ones. Oh, and while you're doing that, quiz 3.2, come back.
You put it in already?
I did not. I'm gonna put it in at lunch. I like to give it back to you before putting it in, so you can see. 90 and 80 to 89, anything in the B range is gonna get a sticker. Anything in the 90 plus range is gonna get a smelly sticker.
Never gonna get a smell.
If it's peppermint looking, then it smells like peppermint. If it's a dinosaur, it smells like strawberries.
But hear me out. The one test I got like 104% on, I didn't get a sniff sticker.
Well,
So-
then maybe on a test that you don't get an A, maybe there'll be a surprise sticker on it.
High smelly sticker?
Maybe.
No way.
You said B range. B range is a star smiley sticker. A range. Yeah.
Oh gosh, can I take the product?
That should be everybody. If you took it in person, if you took it online, your grade is waiting for you.
Okay, my life is not together. Okay, yeah, that makes sense now. I'm annoyed about that.
Yes.
Oh, yeah, I love seeing that. I love
Yeah, look at it completely wrong.
Huh?
The
The quotation one? Yeah, I forgot to put X on it.
Like, I want oh my gosh.
I know. Your dreams have finally come true. Smell it. It smell good?
It smells so good.
Strawberries?
It smells like strawberries. I got approved.
Yeah, I was agreeing, like, the X squared, like.
I like how-
If it was instead like 4 times x to the third, and then like times 3 times x squared, and they were all just numbers, not attached to anything. That seemed to happen a lot. Like, you tried to do more than you could. But you got pretty good at, like, you tried to do more than you could. But this was good, this was basically. So the two is
Wait, so
supposed
there's
to-
only one dy right? Oh, no, I just stupid.
So in general, the front went well, and the back went less well. Oh, you deserve one. Let me get you one. I'll even let you pick the color. I'll be bringing you.
My allergies said no.
No. Oh, no. So the. Yeah, so we'll do that. What's the color? There you go. You did well. Dan, you did really well. Well, it's nice to see that some of us had one of our best showings on this last one, so that was cool to see. Calculus is getting harder, and a lot of you are really stepping up to it. And even if you struggled and maybe got something like in the 30s or like the low 40s, you still had a really good understanding of what's going on, and that's awesome. You know, some of the simplifying might have been a little bit tricky, but in general, I thought this was really well done as a class. So, good job. Let's do it. Let's see. 3 and 4 coming at you. Ooh, looks like.
Wait. Sorry.
Take a picture.
Sorry.
Take a picture of the last one.
It will last long.
Boom, face, bro.
Hey, thank you, sorry.
Yeah, you're welcome. All right, let's do it. Looks like product rule twice, yo.
No. This is this one kind of like.
ddx of x squared y plus ddx of y squared x, and then ddx of thing.
Oh, this one does?
Product rule, so u dv plus v du. There's that one. Plus, I don't really need the parentheses, but just so you see it, u dv plus v du. That's all multiplication there. It's not.
What is the alliance?
Oh.
Wait. Oh, never mind. I think it's funny that you still think they're funny. I think you're funny.
It's all about how much time
Remember that one time you just tackled the house?
Finally, oh my god, it took me 3 years to actually accept that I actually did that.
That hurt so bad. I hit the ground so hard.
Yeah, you stole my phone.
Yes. What were you writing on your phone that I could have? Like, were you talking smack about me?
I guess you'll never know. I guess you'll never know.
Probably talking smack to me to Kennedy.
That's basic.
Kennedy?
Yeah.
No, I don't know. You know
Probably
what?
like, she's so dumb. Like,
Oh,
she's bad at
I don't think
it.
what does? Yeah, you're right. That's
Y squared times 1 plus x times 2y dy dx. Yeah, it's bigger than I wanted it to be. There we go. U dv plus v du.
What's the name gonna be? You have to name it.
It's really confusing.
Factoring and dividing.
No, like, I was doing so well.
You went too fast.
I just ran a little bit out of space, so I wanted to have the answer super visible. So I factored out dy dx and then divided by what was it?
Yeah, I'm actually caught on just the negative 2xy part.
Ah, yes, okay, so this doesn't have a dy dx, so that's gonna move over. 2xy gets subtracted from the left, and y squared needs to get subtracted over.
What? How did you get 2xy? Negative 2xy. Sorry, you're
No, you're okay. I want you to get it.
Yeah.
Okay. X squared dy dx plus 2xy plus y squared plus 2xy dy dx equals 0.
I agree.
X squared dy dx is gonna stay. 2xy dy dx is gonna stay because they're all on the left. Everything else is gonna move over, so I'm gonna subtract that. I'm gonna subtract that.
Oh.
I've given up.
I will factor out dy dx and divide by.
Okay.
This is a lot of math.
Thanks. I'm glad you think so. All right, I'm short on time, so I'm just going to differentiate both sides. U dv plus v du.
Wait, there's no like, there's not another dy dx, right? It's just not-
Right, so that's actually kind of nice that I can just move that over. So let's make it look nice. Negative 2 sine x sine y dy dx. Make it nice. 2 cosine x cosine y equals 0. Move that over.
Oh, you have to move that whole thing over. Oh.
Move all this, so negative 2 cosine x cosine y. And then let's divide. It's already factored, so I don't have to worry about factoring. Negative 2 cos x cos y over negative 2 sine x sine y.
Oh, you can go back.
What do you see? Anything we can get rid of?
No.
It's negative 2 cos x cos y over negative 2 sine x sine y.
That's negative 2.
Okay. What's cosine x divided by sine x?
Tan. No, tan tangent. Oh, that's so embarrassing. I got that wrong with the test.
You and like 15 other people.
I don't know why. I was like,
Cotangent x cotangent y.
We were like talking about the test, and I go,
yeah, did you get my cotangent for this?
Thanks everybody. Have a good day. I'll see you tomorrow.
Tangent? And I said, yeah, cotangent.
It's up on your 8.
I made fun of
Cosine x over sine x. Yeah.
She's like, what?
Please.
There was a comment. And I'm like,
I literally made it so much more difficult.
Right.
But I'm in love with number. I haven't been able to keep my eyes off them this year.
So this was another gift from a different student that saw this, and then she ended up bringing in this one. So these are my
You're so much. She said, oh, you gotta put your video from the
I know I saw. I know.
They took
I
over
just
from
like,
them up
I
there.
didn't put this one.
About a few.
From the lizard cage, maybe.
I know.
It's too hot.
It's not ready.
How's that? Yeah, good. Bye, everybody. See y'all.
Nice.
Yeah, cotangent x, cotangent y. That's a nice one.
Yeah.
Sometimes simplified nice.
It's still cool.
Yeah, so I saw so many tangents on that problem. I was like, oh.
Bye, Rosie.
I don't even know.
Bye,
To be honest, I don't even know what I did on that problem. It's kind of embarrassing, but it's fine. I was like, hey, I didn't
Just
put it on the
quotient,
back.
I like tried to pick a nicer quotient rule, like the ln of, what was it, cosine of x, right, or something?
Ellen.
Because ln is so nice, it's just derivative on top, inside function.
I know. I think I
The log
just.
goes away.
I did the product rule. I don't even know why.
Yeah.
It's like I actually did better on the back side than I did on that
Really?
one question.
Nice.
Like,
That's where most of the points were. It's 24 points on the
I
front,
know.
26
I got, like,
points on
2
the
points
back.
are off
So.
and I just simplified them wrong.
No.